Hello. In this lecture we will discuss another AES encryption method called CCM, which is one of the methods used to encrypt IPsec communication. This was defined in RFC 4309. This encryption method does both the encryption and integrity by using the same protocol. You don't need to have an authentication or hashing protocol added with this encryption method, as it is included. CCM is used with AES cipher for encryption, and counter-block chaining cipher for integrity authentication. We will see how this works in details. So, what is CBC-MAC? This is the component used in CCM for integrity, to ensure that the cipher text didn't change in transit. This is called combined mode encryption. The last lecture we discussed AES counter mode. CTR mode doesn't include the integrity piece and would require an authentication protocol like SHA-1 or others. It also uses additional authentication data to ensure that integrity is maintained within a specific IPsec security association. So, the similar portion of this AES method and the counter mode is the method of producing the ciphertext from the plain text. This doesn't change from AES counter mode to AES counter with CBC-MAC. The initiator still issues an initialization vector for the packet. This would get used to XOR the plain text. Now, the same as we discussed in the last lecture, the ASCII IDE is used to generate the encryption key and the nonce. The nonce is consistent across all packets belonging to the same IPsec security association. The sender splits the plain text into 128 bits blocks. It will take each block and XOR it, with the unique counter, which is the concatenation of nonce, the initialization vector, and a counter. This counter starts from the value 1 to n plus 1, where n is equal to the number of 128-bit chunks of plain text. Okay, the difference is the integrity calculation. Basically, the integrity calculation uses encryption as well. It uses AES encryption. So, what happens is the integrity process starts with compiling additional authentication data. In CCM, this is the SPI for this IPsec traffic, concatenated with the sequence number of this IPsec packet. This starts the integrity calculation with a unique value, unique to this IPsec, SAN sequence number. Now, this additional authentication data is XORed with ciphertext block 0 as a starting point. Now, this ciphertext 0 is XORed with plain text P1, and then encrypted with the same counter key used for encrypting the plain text. However, this is not encrypting the plain text, it is encrypting the ciphertext, which is mixed with a unique additional authentication data. Now, each block will take the ciphertext of the previous block, XOR it with the plain text of the current block. It will encrypt it with the counter key. One thing to be aware of is the fact that this value is carried over across the rounds of plain text encryption with the ciphertext. The final round produces message authentication code N. This MAC N gets encrypted with ASCII IDE, and the outcome is appended to the packet, which will be the integrity check value for this packet. The encryption of the plain text follows the same process that was discussed in the counter mode. It is a counter mode operation still. The plain text blocks gets XORed with the counter key and then encrypted with ASCII IDE. The ciphertext outcomes are all concatenated together and will be the encrypted payload in the ASP packet. The initiator then adds the ASP SPI, which would help the responder find the keys used for this ASP packet by checking with the Security Association database. This packet gets received by the IPsec peer. The first step the stack would do is check the SPI. This is used to check the Security Association database to get the ASCII IDE used for encrypting this traffic. The first step will be used to decrypt the ICV, which would get the value of MAC N. Now, the decrypt of the payload can start. The encrypted ciphertext is split into chunks of 128 bits blocks, and each gets decrypted using the ASCII IDE. The stack will then get the nonce value from the Security Association database. It will get each ciphertext block, decrypt it, and then XOR the outcome with the counter key, which would turn out the plain text chunks, 0 through n chunks of plain text. Once all the blocks are processed, this is the plain text payload. Now the recipient wants to validate that the ciphertext was not changed in transit. It will take the additional authentication data, and will run the same operation that we explained. The same operations done by the sender. That is, it will take the additional authentication data, which is the SPI and the sequence number, it will XOR it with ciphertext block 0. XOR the outcome with plain text 1, encrypt with the key for P1, and so on. The last round produces MAC-N. This MAC-N value has to match the value of the decrypted integrity check value that was in the received packet. If the two values match, that means the ciphertext wasn't changed in transit, validating the integrity of the received payload. Hopefully this was helpful. We will discuss more in the next lecture.